this video in response to the Breakthrough Junior Challenge 2015. In this video, I will be explaining you about the flow of charges in a wire. I have chosen this concept because many students have been misled due to incomplete knowledge, and I will be throwing light on how this exactly happens. But there is still some dark phases where we don't know exactly what's happening. But I will do my best, and I will explain you in 3 different timelines with the development of the physics from the discovery of electron to the quantum theory. Let's delve into the concept and see what it's all about. Flow of charges inside a wire. The first idea. In a general circuit, we have a voltage source that may be a battery, a load which can be a bulb, a switch, and a conducting wire. In this type, the current flows according to the conventional from plus to minus when we didn't know about the electrons. But when the electrons were discovered, we knew that the electrons traveled from the negative terminal, that is the low potential energy terminal, to the positive terminal physically from the conducting wire while passing through the bulb, and this way energy was transferred. But there was a problem with this idea. Electrons don't have such empty spaces to pass through very rapidly. They have many atoms and other electrons to which they bump and decrease their speed. Then how did electrons travel so fastly so that whenever we switch on the key, the bulb simply lights up? How was that possible? As experiments were conducted, people came with new conclusions. The second theory was developed on the basis of structure of atom, and in this theory we will also see how the electric field of an electron affects the other electrons. We know that every charge has its own electric field, and this is the case with the electron too. It has its own negative field, and we know that like charges always repel each other, and this is due to the field interactions of both the electrons. So the second theory says that this is a conductor, and this is the negative terminal, this is the positive terminal. So electrons flow from this terminal to this terminal. Then how do they flow? We know that we have an excess of electrons on this side and deficiency of electrons on this side. So electrons jump into the next atom, and because the atom is now unstable, it shifts its electron to the next atom, and the next atom then shifts its electron to the next atom, and this reaction and this type of changing continues until we reach the positive terminal. And here we can see that electronic fields are interacting with each other. To understand our second concept very clearly, we will take an example on the Rubik's Cube. Let's see here. Let us assume that each of these spaces represent the electric field of an electron, and each electron is just a tiny speck in the middle of these faces. So what happens when a potential difference is applied? Let's say this is the negative terminal and this is the positive terminal. So electrons will like to go from this side to this side, and when they want to go, they will push these electrons. So when this electron travels like this, you can see that it also pushes the other two electrons, because these fields are interacting with each other and causing them to repel. So this way these two electrons also get pushed when these electrons are pushed by the negative terminal electrons. So this way we can see that electric fields interact and cause the electrons to move in the direction to the positive terminal. Let's see our third idea and what it is. In the third idea, we have a circuit with the AC power source here. So we know that current will one time go in this direction, and the next time it will change its path. So there will be a plus sign at one time and minus sign on the other side, and they will be changing their directions. So we know that an electron faces many different obstacles in its wire, like the other electrons and atoms. So scientists figured out that electrons moves in a wire but with a very slow speed, and they called it the drift velocity. In this velocity, they figured out what was the net displacement of the electron in a particular amount of time. For example, if you wait for an hour in a copper wire, in a standard copper wire, you will see that this electron has moved in a direct current, of course, only 3 inches, and its drift velocity is therefore 3 inches per hour in the copper wire. So we know that whenever we switch on, electricity travels at the speed of light and the object turns on immediately. For example, I switch on a light, it immediately turns on. If I switch off, it immediately turns off. Then if electrons travel at such a slow speed, then how does the electricity travel at such a high speed? And how can we explain it? Let's see how it happens. We know that now potential difference is applied and electrons travel through this wire, and they travel in a very zigzag manner, going in random directions and bumping into other atoms and going everywhere in the wire. But there will always be a net displacement. And now I have drawn here a AC symbol, which symbolizes that one time the electron will go there, then the other time that will come back. So overall, we can see it as a vibration, but there will be a change in its velocity, which means it will accelerate, and we know that any accelerating charge produces electromagnetic waves, and this is how we can explain it. For modern scientists have found out that whenever electron is accelerated, it transfers the energy, and this energy transfer reaches closely to the speed of light to the load to work so that it may work. For example, whenever we switch this circuit on, this electron will travel in a zigzag manner. Then it will produce the electromagnetic waves, which may probably strike the other electron, causing it to accelerate. The other electron may again produce the electromagnetic waves, which travel through the wire, probably without harming the other electrons or the nucleus of the atom, and come to the resistor, and there they will do the job. What happens in a resistor when these electromagnetic waves come here? When this electromagnetic wave will come and it will hit the electron of the resistor atom. Let's say it may be a bulb. Then this atom will be of tungsten. When that electromagnetic wave comes, it probably hits this electron, and when it hits this electron will enter into an excited state and will go to the next shell. But we know that it will instantaneously come back, and if it comes back, there will be a decrease in its net energy. Where does that energy go? This energy will be emitted in the form of another electromagnetic wave, which we know as light. And we also know that light, along with light, other electromagnetic waves such as infrared waves are also emitted when the electron comes back to its original shell. Let's summarize what we have seen in this video. We have learned two major points. The first is that electrons don't travel physically from one terminal to the other terminal. Instead, they travel only a small fraction of the conductor with a velocity known as drift velocity, and this velocity is very slow even for good conductors such as copper and silver. Second thing, whenever these electrons are accelerated by the potential difference applied to them, these electrons emit energy, probably in the form of electromagnetic waves, which travel close to the speed of light, reaching instantaneously to the resistor and acting upon them by exciting their electrons. These resistors then in turn do the job by emitting the other electromagnetic waves or whatever we want them to do, depending upon what appliance they are. Now, scientists are still struggling to find exactly how this mechanism works, because electrons are so small that we cannot observe them, and how this energy transfer takes place, and what other forms of energy are there than the electromagnetic waves. So it is still an area under research. Thank you for watching this video under Breakthrough Junior Challenge 2015.